Let's look at this example. We're going to find the volume of a solid obtained by rotating a region about an axis. We're going to sketch the region, the solid, and a typical disk or washer. Our region is bounded by y equals 1 over x, y equals 0, x equals 1, and x equals 4. Now, I mean, here we're told to sketch the region. I don't really see how to do this without sketching at least the region. I'm going to make very clear our boundary curves. And this first one is y equals 1 over x. And the second one is, I'll use pink here, y equals 0. That's, of course, the x-axis. The third one is x equals 1. That's a vertical line where x is equal to 1. And then x equals 4. And I should label at least, I should give some indication of scale on the x and y axes. So the region that we're talking about is the one that's bounded by all 4 of these curves, I suppose. And I've just realized that to sketch the solid and a typical disk or washer, I've placed this poorly. So I'm going to bring this down here. Now, the typical disk or washer is just going to be a vertical or vertically oriented rectangle here. Okay. Or it's based on a vertically oriented rectangle. The typical disk, I guess, would look kind of like that. I'm going to fix this. I guess I'll show you how I'm going to fix it. Okay, so I'm going to draw one circle here, and then another circle here, and then do that, and then maybe like, there's my disk. The solid is going to be what happens when we rotate the entire region about the x-axis. And so the solid is going to end up looking like this. And I'll give it, there, some contour lines. And that last one looks off. There. And I'm showing you this as I do it because it's not automatic that it happens right. And it's good for you to see, like, this process isn't the simplest thing. So what happened was my disk didn't extend to the bottom of what I was calling the solid there. So there we go. Okay. Well, let's hope that was the hard part. Folks, we're finding the volume of this thing. And in this case, we're using a disk. And because of the way our representative rectangle is oriented, we're going to be integrating in terms of x. Our region of integration is given by these lines, but we can also see it in the graph here. X is going to go from 1 to 4. So the volume is going to equal an integral from 1 to 4 of pi. Now, I mean, I'm going to keep going, of course, but when I'm thinking a disk, I'm thinking about pi r squared. And so pi and then r squared. R is given by the function height, right? So in this case, it's pi times 1 over x squared. And the thing that's going to give us a volume and not an area is the width of this disk, right? So dx, it's actually a dimension. If you can remember pi r squared times, let's say, delta x, then you basically have this. The rest of it is just figuring out what the pieces are from a picture that you draw. And the integral is, I mean, it's pretty straightforward here. We're integrating using the power rule, right? So my integral is going to be pi. This is 1 over x squared. So using the power rule, it's going to give me 1 over x times, or excuse me, so I added 1 to the exponent. Now I need to divide by the new exponent. So that now becomes negative. And then I'm going to evaluate that from 1 to 4. You can see that this is going to be 3 pi over 4. And there's the volume of this, I don't know, horn-looking thing. Our next example is going to be a little more interesting. Our region is defined by the curves x equals 2 minus y squared and x equals y to the 4th. We're going to rotate this region about the y-axis. Here's our region, bounded by the graphs of x equals 2 minus y squared Now that's a parabola that opens to the left because there's a negative in front of the y squared, and it's moved to the right 2 units because of the 2. And bounded by x equals y to the 4th. If I've drawn my graph well, then I can see the coordinates of the points of intersection, but just in case, let's set 2 minus y squared equal to y to the 4th. And we'll get that y equals plus or minus 1, which agrees with what I thought I was drawing. Now we're rotating this about the y-axis. So my representative rectangle is going to be horizontally oriented. I haven't really mentioned this already, so I'm going to take a moment and mention it now. For all these rotations that we're doing in this series of videos, the representative rectangle is perpendicular to the axis of rotation. Even if there's a gap, it's perpendicular to the axis of rotation. And in the previous example, the representative rectangle was perpendicular to the axis of rotation. So here, I have a vertical axis of rotation, which means I want a horizontal representative rectangle. This leads me to 2 things. Number 1, because there's a gap between my region and the axis of rotation, I'm using a washer. Number 2, I'm integrating in terms of y and not x. So with that in mind, I'd like for you to set up and then evaluate the integral that gives the volume for this situation. Come back when you're done. So we're based on pi times like an uppercase R squared minus a lowercase r squared, right? Outer radius minus an inner radius times a delta y. And our integral goes from 0 to 1. The outer radius is the rightmost one, right? Remember, when we are horizontally oriented, right is bigger than left. So I have 2 minus y squared, the quantity squared, minus y to the 4th squared as my integrand, all of that times dy. And I'm using symmetry. So I've changed the lower limit from -1 to 0, and then I doubled the value of the integral. And what I'm really doing is I'm just taking like the top half of this region because the bottom half is symmetrical. Anyway, after the algebra and integrating using the power rule, we end up with 248 pi over 45.